Hello and welcome back to Calculus 1 lesson 4.4 part 2, right, on graphing functions. So we're going to work on other two examples. We said we have this list of things that we have to calculate, the domain and X intercept and asymptotes and derivatives and first, second derivative tests, right? And we have all of that. We are able to draw the function. So now we have seen polynomial, we have seen rational function, radical function, well, 1 over x squared was easy, and we had seen ln, logarithmic. Let's talk about one of the rational functions, and let's take a look at problem 33. It looks interesting.
The stream is enough.
Thank you.
I mean, it was on this whole time.
Magic, there we go. Great, so f of x is equal to x squared plus 12 divided by 2x plus 1. So this is our function. We start with the domain. Domain is going to be everything except negative 1/2, right? You take the denominator, set it equal to 0 to find the bad values, right? Because you don't want the denominator to be 0. So when you solve this equation, x equals negative 1/2, your domain is negative infinity to negative 1/2 union negative 1/2 to positive infinity. Then we move to number 2, the x intercept. We set y equal to 0, so x squared plus 12 divided by 2x plus 1, everything equal to 0. When you cross multiply, you get x squared plus 12 equal to 0, and this immediately has no solution because you see that it's x squared, right? So it's positive, plus 12, that's even more positive, so it can't go back to 0. So no solution there. That means no x intercepts. Okay. Means no x intercept. Now y-intercept is you set x equal to 0, so that's 0 squared plus 12 divided by 2 times 0 plus 1. The whole thing is 12. So we do have a y-intercept 0, 12. So that's a piece of information that we are going to graph. Number 3, vertical asymptote. Well, we see that our domain is interrupted, and it's interrupted exactly where the vertical asymptote is, because we have 2x plus 1 equal to 0 in denominator. X equals negative 1/2. So I have vertical asymptote at negative 1/2. Great. How about horizontal asymptote? Well, for horizontal asymptote, you can do limit x goes to infinity, and you take the x squared plus 12 divided by 2x plus 1. And if you divide by the highest exponent everywhere, you are going to get what? We're going to get infinity, right? So this is infinity, so no how. Slant asymptote? Yes or no? So this is the only case in all of mathematics where you have slant asymptote, which is why I picked it. when you have a polynomial divided by a polynomial, which we call a rational function, and your degree in the numerator is by 1 higher than degree in the denominator, because they're going to divide into a linear line, which is slant asymptote. This is the only case. You can't have a slant asymptote with square roots. You can't have them with e to the x, ln x, trig. Nothing produces slant asymptote other than the case when you have polynomial divided by polynomial, when the degree on the top is by 1 bigger than the bottom, because now when you do long division, they're going to reduce into a linear line, and the slant asymptote is a linear line. So now we have to do long division of polynomials to figure out what the slant asymptote is. So, here in blood, yes.
The denominator with the numerator exponent is 1 larger than the denominator.
Yes, because it divides into a single x. If it's bigger by 2, then divides into a quadratic, and your slant asymptote cannot be a quadratic parabola, right? So we divide this into x squared plus 0x as a placeholder plus 12. 2x into x squared goes 1/2 x times. 1/2 x times, so this is going to give you x squared plus 1/2 x, and then we subtract, these guys cancel, and you get negative 1/2 x, and then you drop down plus 12. 2x goes into this negative quarter time. Negative quarter times 2 is negative 1/2 x, and then minus 1 quarter. We don't care to calculate remainder or anything like that, because we already have y equals 1/2 x minus 1 quarter. It's kind of a shame that I only have one example in a book, so you're probably going to run into the ones in the homework online. If you want me, I can come up with a few of these for you to enjoy. But we do have slant asymptotes, and we also had vertical asymptotes, so that's great. Number 4, we are going to take the derivative of this. So f prime of x is equal to, now if you use logarithmic differentiation to make your life easy for the first derivative, then you would still have to multiply everything out to do the second derivative. So it's more like pick your poison. I don't usually, I don't do the logarithmic differentiation on a first derivative, because when it gives me the factored answer, I still have to multiply the factored answer so I can do the second derivative. So I will use quotient rule on the first round, and then I would use logarithmic on the second. But you can do both, it's fine with logarithmic. So 2x plus 1 times the derivative on top is 2x minus x squared plus 12 times the derivative of the bottom, which is just 2. So now to simplify this, we are getting 4x squared plus 2x minus 4x squared minus 24. That's what I said. Please pay attention. Thank you. Divided by 2x plus 1 squared. So the first derivative is 2x squared plus 2x minus 24 divided by 2x plus 1 everything squared. All right. Yes.
I think it's minus 2x. Oh my god, I have my negatives back. Sorry.
What happened?
I had my negatives backwards in my head.
So do I need to change?
No, I'm just like...
Oh, okay. Whew. Right, 2. I'm going to kick 2 out just to have x squared plus x minus 12 over 2x plus 1 squared, just because I can. And this is my first derivative. Gets the box. Now I have to do the second derivative. And the second derivative, this is where I go with logarithmic differentiation because lazy. 2x squared plus x minus 12 divided by 2x plus 1 squared. And now the second part is x squared plus x minus 12 and then 2x plus 1 on top. Minus 2 times, and then this is going to be 2x plus 1 and then 2 on top. There we go. Can I make this prettier? Nah, I'm just gonna make this into a 4 over here and that's it. I don't think we can do anything else. So our second derivative is not as pleasant as the first, but at least we have it. Number 5, first derivative test. So we take our first derivative, which is 2x squared plus x minus 12 divided by parenthesis 2x plus 1 everything squared, and we set that equal to 0. 2 immediately cancels when you divide into 0. Denominator dies when you cross multiply. So the only thing that you are focusing on is x squared plus x minus 12 equal to 0, and that one factors into x plus 4, x minus 3, from where x is negative 4 and x is 3. Now, remember that I have a vertical asymptote. Where was my vertical asymptote? At negative 1/2. So I have partition at negative 4, partition at negative 1/2, partition at 3. From negative infinity to positive infinity. My test points, let's say negative 5, 0 as the easiest to compute, 1, and then 4. Oh wait, 0 is here, not 1. That was supposed to be negative 1. Hold your horses, or whatever you have. Switch that. So negative 5, negative 4, negative 1, negative 1/2, 0, 3, 4. Good. Now we're good. First derivative calculated at negative 5. Kill me now. We don't have to worry about writing the 2. We don't have to worry about denominator that it's squared. It's always positive. All I need to figure out is negative 5 squared plus negative 5 minus 12. That's the only thing I have to figure out. The 2 in front is positive. The denominator is positive. When you start multiplying and dividing by positive numbers, the result doesn't change. If you multiply positive into positive, the answer is positive. If you multiply positive into negative, again, it's negative. So it doesn't matter. So we just look at upstairs. We look at the numerator. So that's the 25. Minus 5 is 20 minus 12. 20 minus 12 is 8. That's going to be positive now. So this is larger than 0, and we have increase. Then we go and take a look at negative 1. I have negative 1 squared plus negative 1 minus 12. This is going to be what? 1 minus 1, 0, negative 12, less than 0, decrease, and there it is, my maximum, my max at negative 4. I gotta get the value for this thing, but, you know, give it some time. The next one that we do is, 0, nice. So that's just going to be negative 12, right, because you're using 0. 0 squared plus 0 minus 12, that's equal to negative 12 less than 0, another decrease. And finally, we are doing this for the 4. Then we can focus on the second derivative. We have 4 squared plus 4 minus 12. This is definitely going to be positive because 4 squared is 16, and then you add and you subtract smaller numbers. So increasing, and we go here, put the arrow up, giving us a minimum at x equals 3. At this point, I can already graph the function without doing second derivative, but we are all in this together. So let's do second derivative. Second derivative test, that was point number 6, right? Yep. Second derivative test for concavity. So what do I have here? Holy nightmare, who came up with this? So I'm interested in, if I multiply this, how much, you know, if I FOIL everything, and so how much easier is this going to be? This is the second derivative test equal to 0. So what I'm going to do is I'm going to drop this 2 because that doesn't do anything. You divide both sides by 2 and just gone, because 0 divided by 2 is still 0. This reminded me of my first time when they kicked me out of the math class in high school, because when it's equal to 0, it's equal to nothing. Why bother solving it? The answer to that question that I posed in class was out. Alright, so now I'm going to multiply this in, and look what happens. This is amazing, right? The numerator and denominator, they cancel on the first term, and one of these cancels, so all I get is 1 over 2x plus 1 on the first one, right? We see that this one cancels there, and then one of the 2 cancels here. But I still have to apply all of that to the second one, so it's not woohoo yet. So, but that canceled a lot. And then now when I multiply this in the second one, I have minus, and then this becomes cubed. So I have x squared plus x minus 12 divided by 2x plus 1 to the third power, and that's equal to 0. Now, to solve this, you move the term to the other side. X squared plus x minus 12, minus 12, divided by 2x plus 1 cubed. And if you multiply both sides by the cube over here, so we multiply this side 2x plus 1 cubed, and this side 2x plus 1 cubed. 1 will cancel, so you will have 2x plus 1 squared equal to x squared plus x minus 12. This is 4x squared plus 4x plus 1 equals to x squared plus x minus 12. Put everything on a pile, 3x squared plus 3x, and then plus 13. Great way to ruin everything. I'm sorry? Yeah, the 13 really ruined everything, because I was hoping to, you know, factor out 3 and then have everything. Such is life. So, should we try and FOIL this at 39? 1 and 39, 3 and 13, 4, 5, 6, 7, 8, yeah. So this is probably going to work out to be something disgusting or complex. So negative b plus minus square root of 9 minus 4ac. There it is, 12 times 13 negative. Yep, so no real solution. I'm having 12 times 13, right, divided by 6. 12 times 13 is much bigger than 9. It creates a negative number under the square root that will in fact produce complex, right, imaginary values. So answers are not real. Therefore, we don't have any inflection points after 7 hours of doing this. Great. However, we do have a vertical asymptote to partition on. Remember that all of this stuff we're still working on the partition here. So we have a negative 1/2 as a partition between negative infinity and positive infinity. You pick two values, which will be clearly negative 1 and 0, and then you run that through your second derivative machine. The second derivative at negative 1 is equal to, and we'll take the simplified form where I multiplied it through. So it's going to be 1 over 2 times negative 1 plus 1 minus x squared plus x minus 12. X squared plus x minus 12 divided by 2 times negative 1 plus 1 raised to the third power. Now, we don't like odd powers because they preserve whatever the sign is inside, so you have to compute. That's 1 divided by negative 1, so that's a negative 1 on the first. And now these two cancel, and you just have negative 12, but that's going to change this into a positive, divided by, and on the bottom I have again negative 1 so it's a negative 1 cubed, so it's a negative 1. So this is 2 negative, so concave down. F double prime at 0. Well, that's gonna be great. Zero squared plus 0 minus 12 divided by 2 times 0 plus 1 cubed. 0 kills the 2, so it's just 1. And then you have negative 12 and a negative, so that's going to be plus 12 divided by, and this is just some positive value, who cares? You have a positive 1 plus 12 divided by a positive number, everything is positive, so concave up. And now I go and try graph. What do I have in terms of points? Oh, I didn't calculate the y values for these. Brr. Okay, so we have a min and we'll have a max calculations for y. So y is equal to f of what? What am I looking for? I'm looking for minimum first? Okay, what was the minimum? Yeah, x equals 3. Now the function is 3 squared plus 12. You have to compute these things. 3 squared plus 12 divided by 2 times 3 plus 1. That's 21 on top, divided by 7 on the bottom equals to 3. So we have a 0.33. Oh wait, wasn't our... The what? No, this is the vanilla function, right? To calculate y values. I believe that our top point was y-intercept of 12 or something that was, right?
It was 0, 12.
0, 12? That means I need this to go to 12, which means I have to move everything. Let's go here. So 1, 2, 3, 1, 2, 3. That's 3, 3. So our x is our y. Now I need 12. 1, 2, 3, 4, 5. 12. And that was our y-intercept. So the graph is going to go through 12 and then go through 3, 3 as well. Do we have a... Yeah, we had the asymptote at -1/2, right?
Right.
So that's going to be my red -1/2. And then we have something else special?
A slant asymptote.
A slant asymptote. Nice. And that one, if I remember well, was 1/2 x minus a quarter? 1/2 x minus a quarter. Perfect. Minus a quarter is right here. And then you go 1 unit up, 2 units over. So 1 unit up, 2 units over. 1 unit up, 2 units over. So now this is going to be my blue, because you either have a horizontal or you have a slant. Since we use red for... We are already using red. I need the maximum, and that's it, right? Was that a -4? -4 squared plus 12 divided by 2 times -4 plus 1. 4 squared is 1628 divided by -8 plus 1, -7. It's going to be -4, is it? It is, right? No one cares at this point? All right, fine. We have reached the point in this particular class where it's like, yeah, I'm just done. Right. 2, 3, 4. So this is -4, -4. And that's your max, which means he gets a frown. And the other one is min, gets a smile. Good. All right, so what do I have? Well, let's think about it. To the right of the vertical asymptote at -1/2, I see a point at 12, and I see a smiley face, right? So it's trying to go up and hit that 12. But it can't cross the asymptote, so the function is just going to do that. And then it's going to follow the asymptote on the other side. So we are going to start here and then just go and follow asymptote forever. So this blue line will go forever and graph will follow. Now the same thing happens on the bottom, except, guys, you don't have any points. But what you do have is the maximum and the knowledge that it has to follow asymptotes. So it's going to go asymptote, break off, and go back down to follow the red. So the graph should look like this. And now we go to Desmos, and Desmos will show us the same. So what do I have? I have open parenthesis x squared plus 12?
Yep.
Thank you. Divided by, and now we have 2x plus 1, right?
Right.
There it is. Immediately. And they even...
We don't see it. But we see it already.
There we go.
He's there the whole time.
Do we see a negative 4, 4 on this point? Right? There is a gray point here, if you can't tell. Move. And there is a 3, 3 point right there, or min and max. Right, so they're here. You can check all of your problems, right? You complete the problem, and then you go and graph and make sure that it's the same. Trig problem very quickly, because life. Solar flare. That's it. That should be your excuse for everything in life. License and registration. You know you're speeding? Yes, solar flare. I was trying to beat it.
I wonder what they would say.
I don't know. Do you really want to find out?
I mean, I feel like...
Because at this point you are practically begging to be pulled over. We're going to do cosine, sine, or tangent?
Sine.
Sine. It's problem 41. F of x is sine x minus x. Not used to clicking the laptop rather than tablet. There we go. Please don't go and say, oh, x minus x is 0, sine of 0 is 0. It's just a... No, it's not. You can't subtract these x's, because the first x is buried within the sine, and the second one is not. This would be sine of x minus x, and then you get to subtract. All right. So quickly, domain. It's all real numbers because both of these functions go from negative infinity to positive infinity. Number 2, X intercept. Well, X intercept is going to be when I set these equal to 0. So sine x minus x equal to 0. Sine x equals to x. Uh-oh. Well, it definitely happens at 0. So x equals 0. And does it happen again? No. We know that because of the graph. When you draw sine x like this, and you draw the 45-degree line, it only cuts through the origin. So there is only x equals 0, which gives us 0, 0. And this is immediately y-intercept as well. So this is a point that I will be graphing. Number 3, Vahasa, none. Sine and sine function, cosine function, and polynomials do not have any asymptotes. Number 4, first derivative test. Derivative of sine is cosine x minus 1, and then we'll be setting that later to 0. The second derivative of x is negative sine x only. We're going to put the blue one so we can go back to it. Number... Yes?
I just forget why, but why is there no horizontal asymptote with sine?
There are no asymptotes on sine. Sine is a wave, right? That goes like
where it peaks.
Asymptotes are obeyed horizontal asymptotes are obeyed at infinity. So horizontal asymptote only serves the purpose, let's say, for something like that, where the function goes and then starts following.
Okay.
This one just goes up and down, so it does not have any asymptotes. First derivative test, you're welcome. Cosine x minus 1 equal to 0. Cosine x equals to 1. I think they gave us, yeah, they did give us 0 to 2 pi. So domain is R, but we want 0 to 2 pi because they said cut it up at 0 to 2 pi. Now that's important piece of information for me because they say 0 to 2 pi. So cosine, squiggle like this, well, cosine is equal to 1 at 0 and is again equal at 2 pi. So it's exactly the two values which are at the end. So my partitioning now is 0 to 2 pi. I don't have any vertical asymptotes. And now the whole thing is just one partition from 0 to 2 pi. The whole thing is one partition. And I pick a value of, let's say, pi, and I compute that f prime at pi to figure out whether the entire 0 to 2 pi is increasing or decreasing. So first derivative computed at pi is going to be cosine of pi minus 1. Cosine of pi is negative 1 minus another one is negative 2, less than 0, decrease. So there is a decrease from 0 to 2 pi. Now number 6, second derivative, that's negative sine x. Set that equal to 0 and you are going to get now sine x x equals 0, pi, and 2 pi. So for sine function, those are the values 0, pi, and 2 pi where you have your, oh, this is a negative sign, so negative sign, there you go. It doesn't matter because you multiply both sides by negative 1, 0 kills it anyway. So now I have, whatever. So let's do the partition. Partition is between 0 and 2 pi. That's set by the domain, but we also have them here. And then there's a partition at pi. We are going to pick test points pi over 2 and 3 pi over 2 for simplicity. If you like pain, go ahead, go with 5 pi over 24. I don't know. And all I need to do is to compute pi over 2 in the second derivative. Now where's my second derivative? Is negative sine x. So negative sine of pi over 2. Sine of pi over 2 is 1, so this is negative 1, which is less than 0, which means concave down. Then I have another second derivative calculation at 3 pi over 2, which is negative sine of 3 pi over 2, which is sine of 3 pi over 2 is very good. So negative negative 1, that's positive 1. So concave up. At this point, we graph. I don't need this part of the graph at all because everything starts at 0 and ends with 2 pi. Pi over 2, pi, 3 pi over 2, 2 pi. What do I have as my points that I use? I have 0, 0, as a point. My inflection points are at 0, pi, and 2 pi. So I do need the y value for pi. So f of pi is, what are we doing? We're doing the sine problem. So that's going to be sine pi minus pi, and sine of pi is 0. So the whole thing is negative pi. So the point that we are talking about is pi negative pi. So pi negative pi is here. And now move, get more space. All right, so what else do I have? I have 0, 0, no asymptotes, and I have that the whole thing is decreasing, and then concave up and concave down. Okay, so concave down first, and so concave down here. Why? So concave down, that turns into a concave up. Something like that. Going through this point of pi, negative pi. Master Desmos, what do we have? Sine x minus x. Right? Now, I have to just make sure you guys are seeing exactly what you are supposed to see. I need you to see this one. That's your 2 pi value right there as 6.28. So you see it goes there, it changes concavity halfway, so this is concave down and then this is concave up. Right? Because if I trace through this one, I'll be able to create a U which holds the water. From here, which is where the inflection point is, we had that as a pi, negative pi. The other part over here gets to be concave down. Spills the water. Ta-da! That's it. I will take a about 17-second break and then we'll do some exam review. Bye.